Hi everyone, this is Lab 1, Constant Velocity. A quick table of contents is the introduction, main ideas, experiment, computational model, discussion, and conclusion. So the purpose of this lab is to track the position of a car moving along a track at certain time intervals and compare it to the predictions of a computational model to show constant velocity. The experimental measurements were calculated using a video analysis app called Tracker, and the projected measurements were determined with code. The main formulas used in this lab are derived from Newton's second law, and the concept of velocity is from Newton's first law. Overall, the results from both models were similar but not exact. There was a slight deviation that compounded over time, which led to a difference in values at the end of the time interval. So the main ideas are Newton's first law that states an object at rest remains at rest unless acted upon by an outside force. The net force acting on the car must be zero for it to have constant velocity. And then Newton's second law, which is the momentum principle, as shown on the left image. The position update formula is derived from Newton's second law. It's shown in the middle, and it is used to find the car's position after a certain time interval. And then the velocity update formula, which is shown on the right, is also derived from Newton's second law, and it shows that initial velocity equals final velocity if there is no net force. Now for the experiment. So the system in this experiment is the car, and the surroundings are the track. The initial conditions are at t equals 0. The car is located at x equals 0 with an initial velocity of 1.13 meters per second, and I showed the calculations below. We assume that initial velocity equals average velocity for this experiment. So now for using Tracker. To track the time and position of the car on the track, I used a program called Tracker to plot the location of the car at each time step, and that's shown in the first image. Tracker compiled the information into a table of time, x values, and y values, and that's shown in the second image. This information was then used to create a graph with position and time, and that's shown on a later slide. So now for the computational model. To create the computational model, I altered a starter code in GlowScript. First, I changed the initial position vector to match the one on Tracker, and I changed the x component of initial velocity. To find this value, I used the position update formula and solved for average velocity. I also altered the time constraint so that the loop ended at 1.43 seconds to match the time on Tracker. And then I changed the time step to match as well. And then to code the position and velocity update, I just used the two formulas, and the variables were already defined earlier in the code, so I could just plug in the variables. So the output of the code was these two graphs and then the data points below. For the first graph at the top, it plots position versus time. It shows a steady increase. And then the second graph shows velocity versus time, which stays constant. And then the values below print out the position and time at each time step. And I use that data to create the graph on this slide. So as you can see, I have the blue line, which is the Tracker model, and the red line, which is the computational model. And they are pretty similar. There is some slight differences, which will be explained later. So now for the discussion. So yeah, there are some definite errors in this experiment. While using Tracker, it is very easy to plot a point incorrectly, which would alter the data. Also, rounding data could cause discrepancies, and any outside forces will skew the data. Some similarities. The computational model predicted a positively sloped line increasing at a constant rate from the origin. The data from Tracker was consistent with this prediction, yielding a positively sloped line as well. Some differences. Due to the errors mentioned previously, the experimental graph showed some discrepancies compared to the computational graph. This is mostly due to outside forces and user error. What if the axis was flipped? So the slope of the graph would be negative, but nothing else would change. Velocity would still be constant because acceleration is still zero, regardless of the axis. And then what does it mean? It is important to consider the fact that the friction of the car on the track and air resistance must be non-existent for the net force to equal zero in the x direction. This is obviously not realistic to attain, so this leads to discrepancies in the data. Gravity and normal force do cancel out, so the force is 0 in the y direction. Ultimately, the computational model was a good representation of an ideal world where there are no other forces at play, but realistically, this is not the case. Thank you for watching.